Okay, in this video we're going to look at second order ordinary differential equations that can be reduced to first order. Okay, so some second order ordinary differential equations can be readily reduced to first order by making the relevant standard substitutions. We're going to look at two types of ODEs that can be reduced to first order. So we reduce the equation to first order and then we solve it using methods of solving first order ODEs. So if you are not up to speed with those, you can browse through some of our videos on those ones. We've got like exact ODEs, homogeneous ODEs, linear ODEs, separable ODEs. Those are just some of the standard types. Okay, so first of all, we have got ODEs where the y variable does not appear explicitly in the ODE. So ODE is where y does not appear explicitly in the ODE. So if you like, y is absent in the equation. So for these ones, we make the substitution so we let a new variable v be equal to the derivative of y. Then v prime is going to be our second order derivative of y. So this substitution reduces these ODEs to first order. All right, and then the second type, so type 2, is ODEs in which the variable x is does not appear explicitly. So let's write ODEs in which x does not appear explicitly in the equation, appear explicitly in the equation. So for those ones, the substitution, so the first equation of the substitution is similar to the substitution for type 1, but then for the second order derivative, so this is dv dx, by using the chain rule, we'll write this as dv dy times dy dx, and then we notice that this term is exactly the same as that term there. So we're going to write this as dv dy. So if you like, we convert the equation so that we have got an equation of v in which the derivative is with respect to y. So the substitution 2 reduces these ODEs to first order. All right, so we're going to look at a few examples then to demonstrate how these substitutions work. One must note that so what these substitutions guarantee is just that the equation will be reduced to first order. So that first order may or may not be integrable. So, but the examples we're going to go through now will all work out nicely. All right, so we have got 5 examples here. The first one is a boundary value problem. Xy double prime plus 2y prime plus 1. And then now when x is 2, y is 3 on 2. And when x is 1, y prime is 3 on 2. The second one is an initial value problem. The third one is also a boundary value problem. The fourth one, there are no initial or boundary conditions given. And this one is also an initial value problem. So let's get on with the first one. So in the first one, we've got xy double prime plus 2y prime equal to 1. Then when x is 2, y is 3 on 2, and when x is 1, y double prime is 3 on 2 as well. So the first thing to do is just to sort of analyze the equation. So this equation is linear, and then we can see that the variable y is absent. Okay, is absent. So that means this equation is like type 1 from our notes above. So got type 1. So what we're going to do is we are going to let v be y prime, and v prime is going to be y double prime. Okay, so when we substitute into the ODE, so ODE becomes xv prime plus 2v is equal to 1. We won't bother substituting the boundary conditions. We'll just integrate and then write everything back in terms of y. Now then, this you can see is this is a first order linear ODE, but to put it in that standard first order linear ODE, we need to divide by x. Okay, so then if we do that, then the integrating factor is going to be the exponential of the integral of 2 over x dx. So this is going to work out to x squared. And then if we multiply everything by x squared here, then this is going to give us x squared times v. So the derivative of that is equal to x. When we multiply this by x squared, we get x. Then the integral of the left hand side is going to be x squared v. The integral on the right hand side is going to be x squared over 2 plus a constant, let's call it k1. So what we can do now is if we divide by x squared, So v is going to be 1 over 2 plus k1 over x squared. But then we recall that v is y prime, okay, from our substitution here. So then from here, if we integrate again, then we can now get an expression for y. Integral of half is going to be x over 2. Integral of k1 over x squared is going to be minus k1 over x, and then this is going to be plus k2. At this point, we are now in a position to apply the boundary conditions. Okay, if we start with the derivative one, so when x is 1, the derivative is 3/2. So this is 3 over 2. We have the derivative expression just here. So what we're going to do is we are going to substitute x is 1. So the left hand side is going to be 1/2 plus k1. And then the right hand side y prime is 3/2. So this is telling us that k1 is going to be 1. Then when x is 2, y is 3/2. So we're going to substitute that one here. So the left hand side is 3 over 2. When x is 2, this first term here is going to be 1. k1 is 1, so that's going to be 1 over 2 because x is 2, then plus k2. Then if we solve this again, it's going to give us k2 is equal to 1. And so our particular solution for this problem is going to be x over 2 minus 1 over x plus 1. Okay, so that is the final solution for the first example. Then for part B, we have got y double prime minus y prime all squared is equal to 0. The conditions, when x is 0, y is equals to y prime, they're both equal to 1. This equation is nonlinear on account of this term here. We've got y being multiplied by its second order derivative. Well, actually, even this one is also nonlinear. And then this equation does not involve x. So this one is independent of x. Y is there, y prime is there, y double prime is there. So that means we have got a type 2 in ODE. So we're going to make the substitution v equal to y prime. Then y double prime is going to be v dy, no, v dv dy. Okay. So when we substitute, so the ODE is going to be, in the first term there's y, then y double prime is going to be v dv dy, then minus y prime squared is just going to be v squared equal to 0. So for this one, provided that v is non-zero, we can divide through by v. So this thing is going to be y dv dy minus v. Okay. We can handle it like that, or we can alternatively we can factor out v here, dv dy minus v. Then this thing is implying that either v is 0, which gives us a trivial solution, or y dv dy minus v is equal to 0. Of course, our interest is in the non-trivial solutions. Now, so notice here that y is now our independent variable. So this equation is actually linear in y. Is a linear equation of v, which is a function of, well, y. So the integrating factor is going to be the exponential of the integral of minus 1 over y dy. Then this thing is going to work out to 1 over y. Okay, so if we multiply everything by 1 over y here, then the left hand side is going to be an exact derivative. Then if we integrate here, so v over y is going to be some constant a. So this thing is telling us that v is going to be a times y. However, v is dy dx. So what we have is dy dx is equal to ay, which is now a linear ODE of y with respect to x. The integrating factor this time is e to the minus ax. And so if we integrate this, we're going to get ye to the minus ax is equal to another constant, let's call it b. So therefore y of x is b e to the ax. All right, and then after that we're going to apply the initial conditions. The initial conditions are both specified at x equals to 0. Let's start with the derivative. When x equals to 0, the derivative is 1. So we can come and apply that 1 in the derivative equation here, for instance. So notice both y and y prime are 1 when x is 0. So if you apply that here, the left hand side is going to be 1. The right hand side is going to be a times 1. So straight away we've got a equal to 1. And then the other one, when x equals to 0, y is 1. So we're going to apply that one here. So the left hand side is going to be 1. The right hand side is going to be b times 1. So that means both a and b are equal to 1. So our final solution is e to the power of x. Right, okay, so now let's go to example number C. Example number C, we've got y double prime plus y prime tangent x is equal to cosine x. The boundary conditions: when x is pi on 2, y is 1. When x is pi, y is -1. So this equation is linear. This equation is independent of y. So that means, again, we are in type 1 territory. So we're just going to let v be equal to y prime, and v prime is going to be y double prime. The ODE is going to become v prime plus v tangent x is equal to cosine x, which is linear. So the integrating factor is going to be the exponential of the integral of tangent x. Integral of tangent x is ln of secant. So when we work this out, it's just going to give us secant x. So if we multiply this ODE by secant x, the left hand side is going to be v secant, is going to be the derivative of v times secant, and the right hand side is going to be 1. The left hand side is now an exact derivative, so we can integrate it. So we've got v secant x is x plus k1. Then we can make v the subject of the formula here. It's going to be x plus k1 times cosine x, but v is y prime. So if we integrate again, it means y is going to be the integral of x plus k1 cosine x plus k2. Now that integral we can evaluate using tabular integration. So we take the polynomial, we differentiate it to 0, or derivative of x plus k1 is 1, derivative of 1 is 0. We take the trigonometric function and we integrate it repeatedly. So then we match the first to the second. The first pair is always plus, and then the signs alternate. All right. So that means we can now write y. So y of x is going to be x plus k1 sine x plus cosine x plus k2. Then we can bring the boundary conditions. So let's start with the derivative one. When x is pi, y prime is -1. So the derivative is here. So that means this is going to be -1, and we're going to plug in pi here. So we're going to have pi plus k1 cosine pi is -1. Cosine pi is -1, so this is 1 pi plus k1 times -1 is -1. So that means pi plus k1 is 1. So k1 is 1 minus pi. So that's the first one. Then the second one, when x is pi over 2, y is 1. So we're going to substitute that one into that last expression there. So on the left hand side we're going to have 1. On the right hand side, so we're going to have 1 equal. Now remember, we just found that k1 is 1 minus pi, so we're going to have pi over 2 plus 1 minus pi, which is k1, then sine pi over 2 plus cosine pi over 2 plus k2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So this is going to be 1 equal to, we're going to have 1 minus pi over 2 from here, and then plus k2. So this is telling us that k2 is going to be pi over 2. And so our particular solution, y of x, is going to be x plus 1 minus pi times sine x plus cosine x plus pi over 2. All right, there is 2 more to go. We are going to ask you to have a go at these 2 first. So if you just want to pause the video, have a go at D and E, then when you press play, then you're going to be able to access see our solution of D and E. All right, we'll now scroll down to our solutions. So for D, okay, here is equation D. So just looking at this equation, it's nonlinear. It's independent of y. It's also independent of x. So this one, we can either treat it as a type 1 or type 2. We are going to show both solutions. Okay, so as a type 1, v prime is y double prime and v is y prime. So equation becomes v prime plus v squared equal to 0. Take the v squared to the other side, and so we can separate variables here. Integrating, this side is going to be -1 over v, this one minus x plus k1. Then multiply everything by -1. Then we're just going to make this into k2 because it's a constant in a way. So we're just going to write 1 over v is x plus k2, and so v is 1 over x plus k2, but v is y prime. So integrating this then gives us the general solution as ln x plus k2 plus k3. Now as a type 2, so first substitution is the same, but y double prime is v dy dv dy. So the ODE is going to look like this. If we factor out v, then that tells us that either v is 0, which of course is a trivial solution, or dv dy plus v is equals to 0, which is linear, but the independent variable is y. So that means that's going to be our integrating factor. Multiplying both sides by this gives us this, whereby the left hand side is an exact derivative. So if we integrate, we're going to get v e to the y equals to a. So that means v is a e to the minus y, but v is dy dx. So this again becomes separable. If we bring the x's to the left hand side, we keep the y's this side, and then we can integrate. So this side becomes ax plus b, where a and b are constants. This side becomes e to the y, and so the general solution is ln a x plus b. Now the question is, this is the one we found using the type 1 approach. Are these two solutions equivalent? And the answer is yes, because notice that for this one, coefficient of x is 1. So if we write this one in the same form, then it's going to take this form. So for instance, if we factor out a here, so that's going to be ln of a into x plus b over a. Then by properties of logs, this is ln a plus ln x plus k, where k is b over a. And then of course ln a is just some constant. So let's call this k4 plus ln x plus, call this one k5. So which is exactly the same functional form as this one. All right, then let's go to E. In E, we have got a nonlinear ODE. It is independent of y, so we've got type 1. So that's the type 1 substitution. So the ODE looks like this, which is a bit interesting, non-standard if you like. But this is a good practice, because you could get something like this in an exam or test, an ODE that you're seeing for the first time. So what we can do here is we can make another substitution. So if we let u of x be equal to x minus, remember that is v of x there. So that means we're just going to make this a new term. Then we need to rewrite v in terms of u. So if we make v the subject of the formula here, it's going to be x minus u of x. Then if we differentiate both sides with respect to x, then v prime is 1 minus u prime. So if we substitute into this, so the ODE is now going to be the left hand side. Oh well, everything's on the first term is going to be 1 minus u prime. The second term is going to be u squared equal to 0. This is looking a bit better now. I'm going to take the u prime to the right hand side and write it as du dx. Now I can see this is now variable separable. I'll bring the dx this side and the du that side. This we can integrate. It's going to be x plus, say, k1. This one, what differentiates to give 1 over 1 plus x squared, and the answer is that is going to be inverse tan. So this is going to be inverse tan of u. Now if we take tan on both sides, then we can make u the subject of the formula. So u is tangent x plus k1. And then we're going to have to substitute back. Remember, u is equal to 1x minus v. U is equal to x minus v here. So we're going to have to write x minus v is tangent x plus k1, and then in tan v is dy dx. So this is dy dx. So if we make this the subject of the formula, we're going to have x minus tangent x plus k1. We're almost there now. Then if we integrate once, then we have got our y. So y is going to be x squared over 2. Integral of tan is ln secant x plus k1. Then this is going to be plus k2, of course. So that's our general solution. And then we're going to have to invoke the initial conditions. So if we apply the initial conditions, so we are given that when x is 0, y prime is 1. There is our y prime there. So when x is 0, y prime is 1. So that means we're going to have 1 this side. So plugging x is 0, so that disappears. So that's going to be negative tangent k1. Okay, so this is telling us that tangent k1 is negative 1. Trigonometric equations. So this is telling us that k1 must be negative pi on 4. Okay, tangent negative pi on 4 is negative 1. So we have got k1. Then for k2, when x is 0 again, y is 1. So now plugging into this one. So we plug in 1 there. This first term disappears. Then we're going to have minus natural log of secant. It's going to be secant of minus pi on 4. But secant is even. So secant of minus pi on 4 is going to be the same as secant of pi on 4. And then plus k2. Now, secant of pi on 4 is the reciprocal of the cosine of pi on 4. Cosine of pi on 4 is 1 over root 2. So this one is going to be root 2. So this is telling us that k2 is going to be 1 plus ln root 2. We are now in a position to write the particular solution. So the particular solution is going to be Yeah, let me just write it out like this: x squared over 2 minus ln secant x plus k1. K1 is negative pi on 4, so that's going to be x minus pi on 4, and then plus k2 is 1 minus ln root 2. Okay, let's tidy this up. Bring the 1 here, then combine the ln terms, so that's going to be minus ln root 2 secant x minus pi on 4, and so that is going to be the final expression of our particular solution. All right, hopefully this video has been useful. Thank you for watching. You can subscribe so that you get notified whenever we post new stuff, please.